Here's another video to the lecture Intro PDE. In this video we present section 4.2. In this section we solve the initial value problem of the inhomogeneous heat equation. In the last section we solved for the homogeneous heat equation. Now we may write the solution of the initial value problem of the inhomogeneous heat equation as an integral over time, maybe I write S in the interval 0 to t of solutions of the homogeneous heat equation. By using the inhomogeneity as initial values. This is called Duhamel's principle. Okay, so in this section we may only introduce, show or explain Duhamel's principle. And this Duhamel's principle is very similar. It can be considered as an application, as a special case of the method of variations of constants, for linear ODEs. So let me explain this, and then you will understand that Duhamel's principle is really something very simple. Okay, so first I explained the method of variation of constants. Yeah, if we consider let u dot of t equals a times a of u of t plus b of t or f of t. Yeah? So u is a function from some interval to some vector space, and a is a linear map from the vector space to the vector space. Yeah, and f is again a function from the interval to the vector space. So this is a linear ODE. Yeah, linear ODE. Okay, and we look for initial value problems. We want to solve this equation with initial value u of t0 is u0. Okay, and now the claim is, and the corresponding homogeneous equation is, this is just u dot of t is equal a times u of t. Okay, and then the claim is the following: method of variations of constants. Most of you know this because most of you visited the lecture Dynamical Systems. Okay, the claim is, let us of t solve the initial value problem. So homogeneous u dot us dot of t is equal a times us of t with initial value us of s is equal to fs. So we use the inhomogeneity as an initial value. Yeah? Then integral from u to t of us of t ds solves, so this function u of t equals u dot of t is equal to a u of t plus f of t, so inhomogeneous equation. And with initial value 0. Yes. So u of t equals integral us of t ds plus solution of the homogeneous initial value problem Yeah, this then solves the whole initial value problem. Yeah. Moment. For general t0, I should write here t0. This should be in general. This should be t0. And here also. Okay. Now let's do the same. So we do more or less the same. Now, in which sense is the heat equation a linear ODE? Laplacian. Yeah? We make a to the Laplacian. Yeah? Laplacian is a linear map from the smooth functions on Rn to the smooth functions. On Rn. So it is indeed a linear operator, yeah, similar to A, yeah, with the vector space V as the smooth functions. Yeah, of course. Yeah, the assumptions will not be fulfilled strictly, but to explain, yeah, so we cannot really solve by this idea the heat equation, but this Duhamel principle we can explain. Okay. So we make this to a vector space, yeah? When t going over to u of dot t is a function from t in R to the space of functions on Rn. Yeah, and then we insert here x. Okay, so in this way, we may consider the heat equation as a linear ODE in the space, of course it's infinite dimensional, space of functions on Rn. Yeah, the main problem, the problem why we can't use the ODE theory to apply this, yeah, also this operator is not linear and continuous. It's not linear and continuous in any function Banach space. Yeah, and for this reason the whole ODE theory does not apply. The ODE theory does not apply. So we cannot use this picture really to solve it, but we explain now that we really get the Duhamel principle. Now, what is the solution of let's state the theory, and then we see what it is. Yeah, this is now the solution. Yeah, okay. Integral from Rn over phi of x minus y times t minus s times f of y s t and y. Yeah, this function here, this solves. So if we look at this function here, this solves. Of course, it solves u dot of x t minus Laplacian, yeah, minus Laplacian u of xt is 0. Yeah, since this is the solution of the initial value problem, but what is the initial value? The initial value is u of x, comma, if we set t equal s, yeah, this is equal to f of x s. So at s it is really the solves the initial value is the inhomogeneity. Yeah? So this is the completely analogous thing than we had here for the ODE. So this is completely analogous to this US here, to this us. Okay. And now we take the integral, like in the case, yeah, so we take ds, yeah, and this is now our function ut. And then we show that this, now we prove that u of xt solves u dot minus Laplacian u is equal to f on Rn cross R plus, and limit t goes to 0, u of xt is 0. Yeah? This we prove here. Yeah? This we prove. This is the content of this theory. Yeah, okay, this is completely analogous, yeah, and this is called Duhamel's principle, and this is completely analogous what we had in the ODE situation. Okay, so we introduced this function Vs of xt, as I explained, and then we know that solves this, so is continuous, and this implies, yeah, now this implies now we use some epsilon larger than 0, and then we obtain this. Okay, and then we see clearly, yeah, this if we calculate, now very important, u epsilon of xt is equal to integral from 0 to t minus epsilon vs of xt ds. So this is this integral from 0 to t minus epsilon, integral over Rn. Okay, maybe I should call this also Vs here. Vs, and here also Vs. Okay, so this is then this integral phi of x minus y t minus y f of y s dny ds. Okay. And now if we define this, then we know u dot epsilon minus Laplacian u epsilon. This is, now let's do the calculation. Yeah. We have two places where it depends on t. This place and this here, x and t. So if we take here the derivative with respect to t, now then we should insert, yeah, if we take here the derivative, then we should insert f. Then we should insert for s just equal epsilon. Yeah, so then we should insert for s t minus epsilon. So let's do it here. Insert t minus epsilon. So what we get? Yeah, we get integral over Rn phi of x minus y and t minus epsilon f y t minus epsilon dny. Okay, and this is integral over Rn, yeah, and phi of x minus y epsilon f of y t minus epsilon t and y. Now we get limit, if we take limit epsilon goes to 0. Yeah, then we know, yeah, by the theorem before, this goes to, this is just f of, yeah, this is the initial value, so this is just f of x and t. Yeah, then this goes to t. Okay, so we know this, yeah, on Rn cross R plus. So we know this. So on the other hand, we have the second integral here. Yeah, this second integral. Now we make this this convolution integral. Yeah, we make an coordinate transformation. Yeah. So what is the coordinate transformation? What we make? Of course, we call here t minus s. We call s. Yeah, so here we call t minus s s. Also we make z is equal to x minus y. So y is equal to x minus z. And this is the first transformation. And the second transformation here for the ts, we call s prime, maybe I call it s prime, is equal to t minus s. Yeah, then of course ds is equal to minus ds prime, but the if we insert for s 0, s equals 0 corresponds to t, and s equals t minus epsilon. This corresponds to, yeah, then this. So this corresponds to s prime is equal to t, and this corresponds to s prime is equal to epsilon. Now to get rid of this minus, we reverse this. Yeah, so we get u epsilon of x and t. We can also write integral from epsilon to t. Now we interchange. Instead from t to epsilon, we go from epsilon to t, and then we get rid of this minus, integral over Rn. Then we have phi of z s prime, f of x minus z t minus s prime, d and z ds prime. Okay, now we want to calculate the limits. Yeah, and now if we calculate the derivatives, we want to calculate the derivative, the limits of the derivatives. So we see that, yeah, since this is continuously twice differentiable, yeah, for this reason we can interchange this limit, yeah, because clearly we have now u dot of d bar epsilon is the same as if we take first the limit and then the derivative. Yeah, because the derivative only applies here. So if we take the limit, only acts here, and the derivative only acts here. So we have indeed the limit epsilon goes to 0 from u dot epsilon of xt minus Laplacian u epsilon of xt. This is the same as first taking the derivative and then the limit. Sorry, first taking the limit u epsilon of xt. Yeah, and for this reason we indeed get, yeah, this shows that this shows now, yeah, that this function here, that this function really solves the inhomogeneous. Yeah, so this shows that limit epsilon goes to 0 of u solves inhomogeneous heat equation. Now clearly, yeah, if you look at this formula here, if you look here at this formula, then you see in the limit when t goes to 0, this is 0, yeah. Okay. So this is also clear, yeah, that u of x0 is 0, since when we have an integral over a 0 interval, it's 0. Now we may combine this, and if we add the initial value of the original problem to this function, then of course we solve this. Yeah? Before we had here 0, now we add this term. This solves the equation where this is 0, but here is equal to h, and this solves the equation, this inhomogeneous equation, but which is here 0. So the sum solves both equations. Yeah, so we get indeed this solution. Okay, let's recall what we have done today. We presented a method how to obtain purely from the homogeneous initial value problem a solution of the inhomogeneous initial value problem. And we understood that this is completely analogous to the method of variation of constants for linear ODEs. Okay, so thank you.